So hi everyone, for those of you that don't know me, I'm Marco. I'm one of the structural engineers and software developers here at INDUCTA. Today I'll be presenting a new feature we have been developing over the last year and a half, the wall design and schedule inside the RCB program. So this was released last week. If you've updated RCB, you've already got access to it. So it represents 1.5 years of development here at INDUCTA, so that's 4 of us, so that's 6 years of development has been put into this new tool. The goal of this new feature is, just like the column design, to automate repetitive calculations so that we can design the walls quickly and eliminate the transfer of information between other programs and pieces of paper. So this new tool is comprehensive in relation to wall design, looking at all relevant clauses from Section 2, Section 8, shear as beam, Section 10, designing as a column for strength, Section 11, wall, Section 14, the new earthquake requirements, and we fully incorporate the latest amendment, which is amendment number 2. The goal of today's session is to give you an overview of the functionality. So it will just be an overview. So we're not going to we'll go into some details about some things, but not everything. It will just be too much time. The thinking is I give you an overview, and then just to get you started, then once you get stuck into it, then undoubtedly there'll be more questions that arise. So an overview of how the tool works. I'm not going to talk about wall design theory in detail. Certain things will be mentioned, but I'll just broadly talk about the calculation procedure in broad terms. I'll define some key terminology that we use within the tool, and basically define key modeling and design concepts that we want to keep in the back of our mind as we use the wall design and schedule. So ultimately, at the end of today, I want you guys to have confidence to start using this feature, because just opening it up, initially it might seem a bit intimidating, but the aim of it is to get you guys started. So we'll look quickly at the old wall design. This is still in the program for the 2009 version of the code. And we can see this is what we're replacing. Very, very, very simple, rudimentary graphics, simple reports, very few input design parameters. It has been replaced with the following. So we can see already much more advanced. We can look at the model, design the walls in 3D view, in elevation view. We can isolate and create subsets of the walls. We've got many new coloring tools here that we can use to assist us in viewing design results, rationalizing the design, asking the wall design questions like, can I design to simplified method? The design settings, which are partially collapsed in this picture, are available on the right. We can modify the envelope to something different from what's in the model. All of the clauses that we consider are clearly shown here, so as we switch things on and off, we can see what we're considering in our design. So yes, much more powerful than the old tool. The next big improvement is in the reporting. The reporting is much more concise, much more detailed. The reporting is split up into basically it's shown either per clause of AS3600, or it is shown as a design summary, which broadly follows the calculation procedure within the wall design. And we'll go through that later in the presentation. We can see the section view showing any designed reinforcement. Ties are shown if required. Boundary elements are shown and colored, so are critical tension reinforcement zones if they are needed. And here the design settings are expanded. We can see we have many more options. Things that we can switch on and off, things that we consider, and we have many more than before, because the aim of the tool is to give you complete control over what the wall design is doing. As a final overview, the wall design and schedule is incorporating the old wall deep beam stress analysis. So this may look familiar to some. This first principles finite element stress analysis, we put this into the wall design Why? Because there's some cases where designing the wall for strength as a column and as a simplified method is not allowed. So I believe that's for certain height to length ratios. We can't use either of these, the strength design methods, so we have to perform what the code, if the exact wording of the code is, it tells you to do a strut and tie analysis. We don't follow the code to the letter. We don't do a strut and tie analysis. We follow the spirit, and we do a first principles finite element stress analysis and design instead. If we were doing a strut and tie analysis, we would do a stress analysis anyway to see where our compressive and our tensile struts were. So we may as well just use the stress analysis to design our wall. Before we jump into the program itself, I want to discuss very broadly the general procedure of how the wall design and schedule works. And to do that, I will reference something that we're familiar with, that we're hopefully familiar with, the column design and schedule. So this, if you're not familiar with it, that's okay. You'll be able to follow everything I talk about subsequently. But I'm just using it as a point of reference to a tool and a procedure that we're already familiar with. And if you haven't used it, I highly recommend that you do. So for the column design and schedule, how we create a column schedule in RCB is we prepare the model. By that I mean assigning labels, running second order analysis, open the column design and schedule, and then perform a design using some global column design parameters. What I mean when I say column global design parameters is a single set of design parameters that we apply to every single column. We can iterate this process, adjusting parameters to achieve a more efficient design, or we could move on to the next part, the rationalization of the design using column groups. What I mean by column group is a collection of columns that have a single set of parameters applied to them. So these parameters could be worst case or user defined. And then we iterate this design using groups. So this would be the previously what this replaces the step of printing out A3 sheets of paper with reactions, circling columns, grouping them manually based on their reactions and designing them one by one. This grouping is done within the program using column groups. After a few iterations, we achieve a design that we're happy with, and then we export the column schedule for drafting. Next, before I move on to the overall procedure using the wall design and schedule, I want to define a few key terms, and that is analytical wall and design wall. What an analytical wall is that it is the purple wall elements that we create when we create our structural model. So they can be imported from CAD, they can be manually drawn, they have a start point and an end point, 2 points only, and some thickness. And they only span floor to floor as defined, based on the defined floors within the model. The moment that we open up the wall design and schedule, these analytical walls get imported and they get converted to design walls. So a design wall simply is a wall that is going to be designed inside the wall design and schedule. In most cases, the analytical walls and design walls will be the same. In some cases, the program will automatically perform some merging. So potentially, if there are no intersecting walls, if there's no intersecting slab between floors, the program may perform some horizontal and vertical merging based on the merging rules, which are outlined in more detail in the manual. Merging done automatically, but the user can also attempt to do it manually within the wall schedule, and they can also split the walls. So this simple example illustrates this concept. The picture on the left is how this wall was modeled within RCB. It is made up of 4 analytical walls, so 4 wall pieces, the ends touching and drawn on top of each other between levels 1 and level 2. Upon opening the wall design and schedule, the program recognizes there's no intersecting walls, so the walls are merged horizontally, and then it recognizes that there is no slab zone at level 2 between these walls, and it merges them vertically. So the wall is designed as a single piece. The forces that are calculated by the solver, so the 4 sets of forces for these walls, are combined as a single set of forces for this single design wall, and we design and get results for a single wall in the wall design and schedule. So that's the concept of analytical walls and design walls. The overall process now of how we use the wall design and schedule, very similar to the column design and schedule, in that we prepare the model. There's a bit more things that we need to consider when preparing the model, which we will talk about in the example that's coming up. After we prepare the model, we open the schedule, and then we double check, are our design walls correct. So columns, they're simple elements, point elements spanning floor to floor. Maybe they might have some continuity over multiple levels. Walls are more complex. More stuff can go wrong when we import them, so we need to just confirm initially before we start our design that everything looks all right. If not, we go back, we adjust the analytical walls in the model, and open the schedule again. Once we're happy with what's come in relation to design walls, we start our design by checking, applying, adjusting wall design settings. What a design setting is, this is simply a collection of design parameters that is applied to the design wall. So really it's equivalent to the column groups, but with some minor differences, which I'll discuss in the next slide. So with wall design settings, we adjust them, modify them, apply them to different walls as needed, run the design, iterate, and then when we're happy with our design, we export the wall schedule for drafting. So a summary of the similarities and key differences between wall and column design and schedule in RCB. Basically, in principle, they perform the same things. Wall design is a bit more complex, column design a bit simpler, and the other and we have these equivalent settings, which are column groups and design settings. So in principle, they perform the same thing. They are used to rationalize their respective designs. However, column groups are not needed to run a column design. We can open the column schedule, hit run, and we can get results without defining any groups. Design settings, however, must be applied. So each design wall must have a design setting applied to it before running the design. Not to worry, you're not going to have to spend an hour manually applying design settings to each wall. We automatically apply some default settings based on the fixity of the wall, which was modeled. Again, that will be discussed in detail shortly. And the other difference is column groups are a bit more rigid in terms of the design parameters. So in December last year, I released an update to the column schedule that allows column size and concrete grade to vary within a group. However, every other design parameter must match within the group. Design settings are a bit more flexible in terms of what can vary, and we'll have a look at that shortly. So in summary, column groups, which we're already familiar with, are equivalent to design settings, but they just go about the same thing in a slightly different way, and that column groups must be present before the design. Column groups can be done after the design is performed. Design settings must be present before a design is started. So that's enough of the slides. We'll jump straight into the model, and the simple example that we have, a residential slab with a shear core on the back face. If I show the slab thickness, we have 4 lift cores, an area with service penetrations, stair shaft, and then a few of these outlying walls on the side. Typical floor, 8 stories above ground. There were 4 basement levels, but just for the sake of speed of this demonstration, I've chopped off the basement. So typical layout for 8 stories. Before we open the schedule, the first thing that we need to do is prepare the model. And the first thing we check is under settings, models and solvers. are we using the 2018 version of the code? The new tool only works for 2018, not 2009, so 2018 must be set. Next thing we check are our load case natures defined correctly. So load case nature is within input load cases and load case nature. We have to have dead loads, seismic loads, wind loads specified correctly so that, for example, when calculating B to D Q over G factors, we know which load case to get the values from. If we're going to start artificially modifying any lateral loads within the wall design, which will be shown later, we need to specify the correct load case nature for the relevant loads. Closing that, the next thing we check is our envelope. So under input, load factors. Under envelope, fire is important. We have to have a fire case set if we are to perform fire checks. Less important is have the envelope set. So for every other design tool in our software, the envelope is set here. In wall design, we allow you to vary this from the values that are specified here. So it's good to have it set, but for the purposes of wall design, not so important. We can modify it later. For this model, I've chosen to use equivalent static earthquake. I've specified spectral, but I haven't calculated any spectral earthquake forces. It's just equivalent static. And our structure is non-ductile, so as an initial assumption, so a mu equal to 1. So I'll hit cancel, and the next things that we check are our include in design property. Similarly to column, we need to set, well, the default value for every vertical element, be it a column or wall, is to have include design equal to yes. What this refers to is, this allows us to exclude particular walls from being input into the relevant design and schedule tool, be it column or wall. For example, if we have secant pile walls in the basement that we don't want to come into the wall design, we would select them and change the property to no. In this case, we want to design everything, so everything remains yes. Next thing we check, wall fixity. Why wall fixity is important is that based on the fixity that is set by the user, when we import into wall design, we apply some default design settings. So design settings were a collection of parameters. So essentially, a different design will be performed, a different set of design settings applied to the wall if we are to use the default design settings based on the fixity that we modeled. So this is based on this idea, this old school idea, that our shear core will be our lateral resisting, will form our lateral resisting system. So the shear core is fixed. Everything else will be vertical only, a vertical only element, and will be modeled as pin. And let's go to the lower level, and two more things that we need to check in terms of preparation, and one of them is the labeling of the walls. Why labeling is important? If we don't have labels, we can't create the elevations. We use the elevations, we use the labels to create the elevations, and how we create them, we can do it automatically, or we can go edit labeling, assign labels manually. We're asked to specify opening maximum width. In this case, I've modeled the doors floor to floor, so for these walls to have the same label, I need to specify some distance such that when it searches, so I'll just delete everything. It looks like I had labels already. Delete everything, start again, SW, and then selecting the wall, it searches for all walls on this floor and above that are touching, plus that value that I input previously of 3 meters, and they're on the same floor or above that share the same angle. So selecting these ones, it automatically labels each of those wall elements that are modeled, the analytical walls, above and below, and start a new sequence. Just label these with something generic. If we hit exit, for some reason this didn't label, so I'll just put the label in manually. The labeling tool, what it's doing, it just changes the label property of the analytical wall, the wall element. And if we go up a few floors, we can see it's been applied to all walls. So we don't need to check in plan wall by wall. If there was something wrong with our labels, our elevations wouldn't look correct inside the wall design when we opened it. So labeling is done, and next is probably the most important step of the wall design, and so of the model preparation for wall design, and that is we have to start thinking about our end restraints of the wall and the top and bottom restraints. I'll open up the manual, 1 second. There it is, and I'll just touch upon aspects of a much more detailed example I have in the manual, and I'll talk about what we need to consider. Shear cores. Okay. Let's assume that this is the same shear core modeled in a slightly different way. Let's assume it's been modeled as follows. So in a very nice, clean and tidy way, each wall modeled as one piece, so this back wall going the full length of the shear core, these walls at the front basically spanning continuously from their start to end points. The walls are not separated at intersection with other walls. And then the lift in the stair shaft and the service penetrations are modeled basically touching the wall centerline. So easy to mesh, easy to analyze, easy for the solver to handle. The issue is, if we look at this wall here, which in the example is labeled W02, when it gets imported into the wall design, it is basically the importing is undesirable. Why? When the program searches for end restraints, it is only looking for walls that are touching the start and the end points of a wall element. So in this case, because this wall is basically start, stop here, it doesn't pick up that there's a wall intersecting it at this location. So really, the program assumes that L1 is always equal to LW. LW being the length of the wall, and L1 as defined in clause 11.4 of AS3600. L1 is the distance from the restraint to the free end, or if it was this wall, from restraint to restraint. So really, LW, the assumption, based on this assumption, LW equal to L1, the program is creating design walls in this case that are not correct. So here it is, as it's been imported, no restraint recognized, so free end on the side. Restraint is provided top and bottom by the slab, that's picked up. So LW will be not accurate for the design. HW will be okay. It's even worse on the back face of the wall based on the automatic merging that is occurring. Because the majority of this wall is unrestrained by slabs because there's voids, the program merges these walls vertically. So what comes into the wall design, this one single piece, L1 equal to LW of 25 meters, and then unrestrained height equal to overall height of 22.2 meters, so not undesirable. And let's go back to our example. So this represents the ideal way of modeling cores, or just any set of walls with walls intersecting each other in such a manner so that they're imported as design walls correctly into the wall design. And that is, the walls are split at intersection with other walls. So going back to this wall that we were looking at previously, it's now split into two segments. I'm modeling under the assumption here that the lintel, the header beam at the door penetration, will not provide any lateral restraint, so really it's just been modeled going floor to floor as a small nib rather than a single piece with a penetration. These back walls here have been modeled going from intersecting wall to intersecting wall. The other thing that I've done is my stairs are probably going to provide some restraint to these walls on the back face of the lift core. So if I was to model the void, the program would probably do some vertical merging, which would be undesirable, but in reality the stairs probably going to provide some lateral restraint. So I've modeled with some accuracy both of the stairs. And around the surface penetrations, I've been a bit more accurate with the surface penetrations, so that we have this slab, this slither of slab around the sides that's going to be providing restraint to this SW01, SW02 and SW08. If we show the mesh, we've had to be a bit more accurate to achieve this, and as always it's a balancing act in terms of accuracy. I need to model accurately enough to capture my structural behavior, but I can't go overboard. I have to model at a suitable level of accuracy, something suitable, something that this solver can handle. So we don't want to be introducing a whole bunch of meshing errors and potentially causing the solver the analysis to be incomplete, the solver to crash. So that is it in terms of modeling preparation. Oh, one more thing regarding the wall segmenting. Rather than, one way to do it would be to do it manually, so select, right click, split wall into segments. The faster way for shear cores is go on the lowest level, select all the shear cores, go input walls and go to create current level and above. And then when we mesh the structure, it will automatically segment the walls at intersection with other walls, at intersections with voids. So it does that for us automatically if it's part of a wall group. And because it is part of a wall group, it will still be acting as a single unit. Everything will be stitched back together. One other note, it's also useful if we're to be using the stress design that's built into the wall design and schedule. It might switching on save wall stresses for design here initially will mean the run that we do is a bit slower, but it just saves time when we open the wall design and start pulling up the stresses per wall. Again, we can leave this off and then the program will reanalyze each wall individually, or just switch it on for all walls. So let's imagine we've prepared the model, we've gone solve second order analysis, which is already done for this model. We have results. I'll go to wall design. I'll just clear anything that's present already. And I'll open the new tool via design walls here. It's just preparing something on my other screen, so creating my turning my analytical walls into design walls. And where are you? I'm taking your time. There you are. Let's collapse the design settings. We'll come back to this and we'll start talking about some of the things that we see. So all of the walls that we see that we can select, these are now our design walls, and based on the fixity that we modeled, we have some default coloring, which is shown under overview, color by load resisting type. So all the fixed walls in the core, vertical and lateral, pin, vertical only. Hovering the mouse over them, we can select them if we want. Net select works the same as the basically in the working area of RCB, or as all INDUCTA software. And zooming in, each design wall corresponds to a single analytical wall here, spanning floor to floor. If we go to the back face of the lift core, these walls were merged vertically because there was no intermediate slab modeled at the inside the lift. If we didn't like the merging that was done, again, like I said, we could go back, adjust the model, or we could select and then pull up this wall's elevation, show this wall's elevation. Let's switch off the text. We'll come back to that. You can select it, right click and split it into analytical walls. We don't want to do that in this case. We could also select multiple walls and attempt to merge them, but we're not allowed in this case because there's intersecting walls at that junction. So we'll keep it as it is. Let's go back to 3D view and show all walls. Again, an overview of other things that we see here. We can look at the walls in 3D in elevation. We can, as we design, we can jump between the different views. We have these overview tools here, so these help us in rationalizing the job, help us in and basically asking questions. So let's see, if I press this button, this tells me the default design settings are applied. So the design settings are hidden away in here. We'll come back to them. But by default, the shear core fixed has the design setting number 1, vertical and lateral, applied to it. All the walls colored red were pin and have the design setting vertical only applied to them. So design settings were a collection of design parameters. Finally, before we go into more details about what is available to us, I'll talk about this little control here, what this is, design set. Design set simply is the walls that will be designed when we press the design button. By default, it is all walls. We may not want to design all walls every time we make some change, so because it can be a long process. So we start isolating the walls that we want to design, create subsets of them using design sets. So, for example, like in all INDUCTA software, you can double-click the legend, which will highlight elements. For this case, design setting vertical only. I can right-click, make design set from selection. This automatically populates these fields for us. I can do it manually via the control itself, so I can isolate the individual elevation. I can create subsets within these walls, so right click, make design set from selection again, or I could isolate the individual design settings. So just the various ways that we can isolate the walls that we want to query or that we want to design. Okay, so that's a very broad overview, and let's just hit run. Without even looking at the settings, let's hit run and see what happens. So I'm going to design my shear core using some design setting. We don't know what the parameters are, we just know it's called vertical and lateral. So just using the default ones that are inbuilt in the program. It won't take too much more time, and with the design complete, the coloring by results becomes active. So by default, pass fail. If we were to select this button, we can see a bit more information for the ones that fail. So we've got some symbols here. DC, okay, failing for design as column. FR, fire, so these are all failing for fire. And then ST, failing for strength. BM, buckling, moment magnification. So alright, so all of these walls that are failing for buckling, probably 22 meter high column, designing as a column isn't working to section 10, hence failing. Other things that we can look at in 3D, we can look at reinforcement, color by reinforcement that was designed, vertical, horizontal, ties. If we had critical tension reinforcement zones, boundary regions, we could isolate them here. We don't have any because we're non-ductile at the moment. We'll see what boundary elements look like soon. We can also look at the results as text in elevation in a similar way to the column design and schedule. So the text that's displayed, so those are failing, maybe we can skip that. We can see a summary of the information for the individual design walls. So alright, here we see HW automatically calculated by the program as unrestrained height, but it's recognized that they're there is many walls on top of each other with a similar footprint, so overall height h of this wall is picked up as 22.2 meters. And just like column design, we can customize what we see. So we've looked at very broadly, very quickly, the results. We can select individual walls, right click, and we can also view the results as a report. So we can color it in 3D, we can view it as a report. In this tab, it opens a report, shows the section, shows the wall in section, plotting any reinforcement that was designed, any ties if they are required. If there was boundary elements, if there was critical tension reinforcement zones, we would see them here as well, but currently none. Let's expand the report out. Let's see what we see. So the report is split into, it's shown either as clauses individually, so we can go directly to a clause that we have checked to see what's going on. Okay, clause 11.4. Or we could follow the, we could look at the reports that follow the calculation procedure. So we start with, okay, some internal forces, the initial reinforcement based on the clauses that we're considering. So that's controlled via design settings. Still haven't looked at that yet. We'll get to it. Strength summary. So this is strength design as a column. So we've got our values there, governing combinations. The reporting all looks very similar to the column design. That's because it's doing the exact same calculations as the column design, but for the wall. Shearer's wall is done, shearer's beam, which I won't show, core confinement, restrainer, vertical reinforcement. So all shown here in the report as text. So let's go back to design, back to 3D view. Let's color by settings. Well, let's show everything. We've run a design based on some design setting, but we're not entirely sure what those settings were. So let's expand out the design settings and let's have a look at what they are, how we can change things. And let's go here. So by design settings, I mean everything inside this entire tab. So expand it out with this little pin. The active design setting is set via this drop down. The design settings can also be viewed, queried. We can clone them, create new ones via the design settings tab. The design settings tab also gives us a quick way of just seeing what walls they're applied to. So vertical and lateral design setting was automatically applied to these walls based on the fixity. Simplified method design setting exists, but we don't apply it automatically. Our thinking with the design settings is that you will create in the office some default library, which when you create a job for the first time, you read it in and then just start applying them. Let's go back to the design tab. So as we can see, there's many switches, many controls. Why there's so many? Two reasons. Wall design is more complex than column design, and we see it's incorporating section 2, 5, 8, 10, 11, and 14 of AS3600. Plus, there's no, talking to our clients, there's no real, we couldn't find a consistent sort of industry-approved method for wall design. Everyone does something a little bit differently. So we wanted to encapsulate all that, so to give you basically complete control over what's considered, what's not considered in the design. Hence why we have so many of these switches. Before we jump into these switches, I'll talk about the envelope. So we have the design switches, which we'll come back to. We also have the envelope. So the envelope is the forces that the walls are designed for. So here we have vertical and lateral designed for everything. Let's make the vertical only design setting active. And I just want to design it for vertical only. So for design setting number 2, I'll switch off my earthquake. I will hit update. And what this has done, I've changed design setting number 2 vertical only, and every design wall which has design setting number 2 applied to it, these red ones, will now have these parameters. So basically these walls in red will not be designed for earthquake force when I hit the design button. We've looked at that. We've mentioned simplified method, envelope. Yeah. Now let's have a look at the settings in a bit more detail. Let's go back to vertical and lateral, and let's expand out some of these clauses. So the settings, the details are broken up into section properties and switches. Switches broadly follows the calculation procedure, so strength, fire design, shear, earthquake checks, restraint of vertical reinforcement. Hovering the mouse over any of these controls, it should tell you exactly what it's doing. So if it's related to a clause, it tells you, and then depending on its condition, it tells you what it's doing. So here, with this K value switched off, we're checking effective height to clause 11.4 automatically, and if we expand out 11.4, we should see it here. If I was to switch it to user defined, as we see based on the tooltip, these values become grayed out. Clause 11.4, automatic K factor to section 11 is not considered. So not only can we switch off individual clauses, we can switch off entire sections. So switch off fire design, and another example, switching off shear design completely. In some cases, we'll see this applied if required. That is because in some instances another clause might be referencing section 8. So in this case, restraint of vertical reinforcement is on, which is checking if restraint is needed to clause 11.7.4. This references many other clauses which could potentially send you to the detailing requirements for ties of section 8, hence why we see this message in this case. So if I was to switch this off, section 8 would not be considered at all. And earthquake for this default case is on. The ductility, the default value for ductility, comes in from what was input for in the earthquake calculator or in the spectral analysis calculator, what ductility was input when we were calculating the earthquake lateral load. So in this case, non-ductile. Because we're non-ductile, if we go to section 14, only clause 14.4 is applied when earthquake is on. Clauses 14.5 to 7 are not on because currently we are a non-ductile structure. We'll see how we can make modifications to this shortly. So we've looked at very broadly the overview of the switches. Next I'll talk about the forces. The forces that are available to us that we can see, and also how we can artificially modify these forces just locally here within the wall design without having to close or rerun the entire model. So before we look at that, I will just define a few key terms. I'll just isolate this elevation, show this wall's elevation. Sorry, design view. I will color by design setting. No, I will pull up bending moment. I'll look at the X value for the combination, for one of the earthquake combinations. And let's hit value. So just zooming into this wall on the bottom left here, we see under the forces, under coloring by forces, we have a few options. We have analysis, modified, and design. Now it's important to know which one is which. Design is simple. This is the final value that the wall design is using for design, but how it gets there we need to have a look at. So analysis is the force that comes from the solver. So when we hit second order analysis, F7 shortcut, this is the force that the solver creates, the forces the solver has calculated. Modified are user modified forces. So we have a few controls here on the right that can artificially change our analysis force. We'll see exactly which ones they are in a second. So in this case, nothing is changed, so they're the same, and design force. Okay, we see some small change between modified and design. Most likely minimum moment is having an effect. Let's jump back to the manual, go to calculation procedure, internal forces. So the starting point is from analysis force, excuse me, and then next we have user modified. So these are the controls under design settings, design switches that can potentially modify the from analysis force. The ductility can be artificially modified, so ductility with one value can come from the analysis, and we can modify it just internally in wall design using this. We can modify where the axial load comes from, static or area method. We can even switch off. We can switch off out of plane effects completely. We can ignore bending moment and shear if we wanted to for pin-pin walls, for gravity walls. So just making our pin-pin walls effectively act as just axial load only. So those are the controls that affect user modified. We'll see how this functions in just a second. And then finally, when we hit run, when the program creates the design force, so it gets the modified force and it makes some additional changes to it. For example, putting minimum moment on. We could switch off minimum moment as shown here. And in some cases, if it's applicable, minimum shear value may be increased to clause 14.6.6. So again, in our case, they're the same, except for minimum moment has the minimum moment check has increased some of the force on the upper walls. Now, what I'll do is I'll artificially modify these forces to see what effect it has on the magnitude of the earthquake force. Let's remember this number, 2,400 kilonewton meters mx at the base for a non-ductile wall. I'll change this to limited ductile, and we see by switching that on, some of the boundary elements, critical tension zone clauses are switched on. 14.6 has switched itself on as well. And then I'll hit update. Yes. And we lose our design values because design settings are changed. I'll just hit design one more time. And we'll just have a look at what effect changing the ductility has had on these bending moment in the X direction. So because we're non-ductile now, we have critical tension reinforcement zones, boundary elements. We'll come back to that. Let's look at our forces, MV. So analysis force hasn't changed. We haven't run the model again, but the modified force has. Because we've changed the ductility, the earthquake force has basically halved in this wall. And then the design force is the force that will be used in design. So it's the modified force in this wall. And again, looks like minimum moment is taking effect on these upper walls. So that's just an overview of the forces. I've just shown bending moment, but we also have shear, axial force. We have the section stresses just considering vertical loading. We have section stresses considering bending moment as well. And we also have internal stresses, so we can look at the stresses as a mosaic, which we'll see later. We can look at that in 3D and in elevation for multiple walls. Okay, so we looked at the forces. We saw how using the switches available to us in design setting, we could artificially modify these forces within the wall design. Ideally, we should, if we're happy with the design limited ductile, we should go back, change the ductility in our design in the earthquake calculator to match this, but just saves us having to open close repeatedly. We've looked at forces, we've made the shear core non-ductile, and by doing that, the program has created some boundary elements. Let's just look at this elevation. We're happy just looking at this one. Let's switch on critical tension zones, boundary elements, and let's press the question mark. So the program can create 4 different kind of boundary elements, well really 3, and then this 4th one that we call a boundary restraint, and it plots in a different shade of green the extent of said boundary element or region. So in our case it looks like we have rather than the boundary element just being at the wall end, it looks like that it's extending over the entire length of the wall. We'll try to figure out why that's happening. Before we jump in and try to answer that question, I'll just pull up the manual again and mention this chapter. Boundary elements are shown here, and this table broadly explains how we reach how we get to a certain type of boundary element. So for us, we were this olive one. We have ductility equal to 2, less than 50 MPa. Okay, and probably what's happening, we have heavy loading at the end. So we need, and we're greater than 4 stories, so we need this type to restrain to clause 10.7.4. And distance is based on the stress at the ends. I mentioned we have this 4th one called boundary restraint. Why I refer to it as a boundary restraint is that it doesn't come from section 14. This comes from section 11.7.4. Amendment 2, section 11.7.4, they made some changes to it. There's now requirements for, in some cases, lapping U-bars into the horizontal reinforcements at the free ends of the walls. And because it's not section 14, or we fully consider these U-bars if they're needed, but because it's not section 14, because they're not called boundary regions, but sort of doing the same thing in my opinion, I bundled it into the same tool, but just gave it a different name. So you may see when you have non-ductile structures, this, again, it's quite rare. I don't think, I couldn't think of a case off the top of my head where you'd be designing a non-ductile structure with concrete grade, with walls with concrete grade greater than 50 MPa, but just be aware it's in the software. So those are the different types that are available to us. This is broadly the calculation procedure the program is following for the boundary elements. And let's select one of them and try to figure out what's happening. So we'll select it, we'll show wall report. If we zoom in to the section, let's collapse this, we don't need this. We see, okay, boundary region across the entire cross section, we need this many ties. We also have the critical tension reinforcement zone, so if we zoom in, okay, it's telling us we need additional reinforcement in this zone as per the critical tension reinforcement requirements. So at the boundary element, what's happening, let's select the relevant clause. We were limited ductile boundary element, and then this gives us information related specifically to this clause. Okay, so greater than 4 stories, and we have, okay, high axial stress, high compressive axial stress greater than 0.15 F-C over a length 0 to 4.2 meters, and really the length of the wall is 4.2 meters. So that's basically it. The axial stresses are so high across the entire length of the wall that we need to restrain all of the vertical reinforcement as per section 14.6.2. So this is if we're detailing it as a limited ductile structure. Sorry, what was mu equal to 2? Was it limited or moderately? Limited ductile, yes. Let's collapse you again. Let's have a look at the forces. I just want to actually see the forces that are causing this. So we'll go back to design. Let's make a design set just for this wall. Make design set from selection. Let's switch off critical tension boundary elements, and we will pull up our forces with moment. So let's go to envelope and we'll have a look. We can look at the absolute values of the envelope as well, but I'm more interested in stresses as a percentage of F-C, and there we go. So straight away we can see across the entire length of this wall we're greater than 15% or 0.15 F-C, FC being 40 MPa as modeled, hence boundary elements required. So that's basically very quickly we were able to use the reports, we were able to use the coloring tools, the plotting tools available to us to answer the question of why we needed the boundary element. Now we'll do a few more things. I'll ask the software a few more questions, perform a few more tasks, and then I can answer some questions if you have any. So the next task that we will perform is, let's go back to coloring, let's show all of the walls, is I want to design these walls. I want to ask the question, can I design these walls to the simplified method with a single layer of reinforcement? So let's isolate them. Let's do net select or select via here. I can go right click and make design set from selection. So I'm not really interested in the vertical only design setting. I'll just use the simplified method one. So how to assign a design setting, I select it, I make it active, and the quickest way probably now would be to apply settings to design set. So I've already created a design set. Basically I've isolated the walls I'm interested in, and then I could just go apply settings to design set, and now all of these are simplified. Another way would be, again, select them one by one, select them via the legend, and then go right click and apply settings to selection. So that's another way. Or if I had the selection created, apply settings to the selection via this button. So basically applying all of these design settings to these design walls. So simplified method is on. Other settings that we have for simplified method, so section 14 earthquake requirements switched off. I'm ignoring out of plane, so basically just acting as an in-plane element in the XX. And anything else of note, so ductility for these walls is still mu equal to 1. And to ask the question, can I design to the simplified method, I hit this button under overview, simplified method allowed, yes, no. It performs some checks for this design set, and then it colors them for us, allowed, not allowed. So we can see the majority of them, yes, we can, but for 3 of them, no. For some of these buttons, the note tabs opens up and we see a few clauses. We see a summary of the clauses the program has used for the simplified method allowed yes no checks. Clicking here, we don't actually allow you to switch the clauses on off here. You have to click the relevant clause here in design settings. So not obvious instantly which one controls which, but if we go to calculation procedure, simplified method, we've got some nice color coding here. So for example, we had earthquake requirements switched off, so we're not checking clause 14.4.4, which can determine whether or not we're allowed to use the simplified method. Now, selecting the walls, for some of these checks, this little text here is populated and it gives us some information for this wall about the checks performed. So this one was passing, we're allowed to do simplified method, and it gives us a summary based on the clauses. Let's click one of the ones that doesn't work. Why is it failing? Okay, section intention, C clause 11.2.1, 11.2.1 is failing. Okay, so let's try to force it to work for the simplified method. Let's see how far we can get. Most likely what's happening is we have earthquake applied for these walls. Even though out of plane is not considered, we probably have earthquake in this global YY direction, probably creating some higher tensile force in these lower walls. Let's see what happens if we ignore earthquake for the design setting simplified method. So for all these walls with design setting simplified method applied, earthquake will no longer be considered. Let's hit check simplified method yes, no. Okay, so by getting rid of earthquake, we got two of them to, we're allowed to use simplified method now. One of them is still failing. Well, it's not. We haven't designed it yet to simplified method. We're simply checking, can we do it? Still for one of them, no. Why? Okay, so we're still in tension. So most likely, just due to the axial load, we have a high tensile force. Let's have a look at what that force is. So we will show bottom section stresses. In this case, I'm not interested as a percentage of design. I'm just interested in the value. And we don't even need envelope because we just have one single case here. That is our, basically it's just one case that is forming our envelope. The red is tensile forces. We see that every single wall has some small force. Why are these passing? Why is this one failing? Why? Because of this limit here. Ignore tensile stress less than this value. So by default, anything less than 1 MPa tensile is ignored. But this is 1.3, hence we fail. If I was to change this to 2, hit update. Yes. Color by simplified method allowed. Yes, no. Performs the checks again for walls in this design set. Everything is now passing. We are now allowed to design each of these walls to the simplified method. The next question that we wanted to ask was, can we design them as single layer? Reinforcement can be set. We can force it to be single or double. Of course, if it can't be designed to single, it just returns a fail, or automatic. So automatic, it will put double if it's needed. How we check, can we do single double? We check color by double reinforcement required. Perform some checks. And for most of them, we need 2 layers of reinforcement, and these are the checks that are being performed. So section 10 is off because we're not designing as a column, and then these are all of the other clauses that could potentially influence whether we need single double. So earthquake is off, so section 14 is not considered, and these are the other clauses which are shown with their linked control under calculation procedure single double layer reinforcement. So these are the values that correspond to these checks. Selecting one of the walls that passes, it gives us information why it can be designed as a single layer of reinforcement. One of the ones that does not, let's press it here. Okay, why is it failing? Axial stress check less than 3 MPa. Load combination number 1, we have high compressive stress of 9 MPa, well above the allowable limit, hence single layer not possible for this particular wall. So that's just a quick overview of some of the questions that we can ask the program, and then how we can adjust things in our favor using the design settings. So asking questions using the overview tools, and then changing things using the design settings. 2 more things that we'll look at very quickly. Let's go back to our shear core. We'll look at the stress design, this integration of the stress design tool, and then we'll quickly look at the schedule. Let's go by elevation. Let's color by this so it doesn't do more calculations. SW01. So we saw, if we remember from when we first pressed run, these walls were failing because they were failing under buckling. There'll also be some cases where we aren't allowed, just via code limitations, we can't design it either as a column or to simplified method. We have to perform a stress analysis. To do that, we select multiple walls or individual walls. In this case, I'll do one. I'll make design set from selection. I will go to the stress analysis, and then for my envelope, or really I can just keep it as this, I'll just design this wall. As we can see, all these analytical walls are merged. It's designing them as a single piece. And this wall deep beam stress analysis functions the same as it did previously. We can specify some reinforcement. We have some integration tools here as well, as we've always done. And if I pull up the tensile stresses, we can see them here in elevation. Vertical, horizontal stresses are available as well, as they've always been. The new addition to the wall design and schedule is, if I go back to 3D, we have this option here to show internal stresses. Unfortunately for this example, it's not working on my computer, but what we should be seeing is basically a stress mosaic for this load combination per finite element. Now let me pull up, I've got an example here, I've got a screenshot of this, of what it should look like. For some reason it doesn't like this model. Let's go to the chat. Where is it? There it is. So multiple walls in elevation, or more walls in the elevation, color by internal stresses, the Y stress, and then it plots it. It plots as a mosaic per finite element. The other thing that it can do is, it doesn't like this picture, but what you can do, you can specify a range of stresses, so it will only highlight above a certain range. We saw that the program automatically calculates boundary elements to section 14. However, we can also use this, so we can put in percentage of F-C, for example, 15%, and it will highlight the length and the height of the zones where we need boundary elements. So just another way that we can visually represent the location and extents of our boundary elements, but unfortunately not showing for us today. So those are the various ways that we can create design settings, design the walls, query our results using coloring, reporting, looking at things in 3D. Let's imagine that we've designed everything and we're getting ready to export. How we create we can work in elevation view as well, which we haven't done, but the wall schedule is created here in the wall schedule tab. Just like the column schedule, we can specify what is shown. We can export to Excel to DXF. It also gives us some information here. So vertical, horizontal, these dashes mean a design has not been performed. Okay, but what we see here for elevation SW2 is that design has passed. However, we have vertical reinforcement V varies. So what's happening is the program probably has created different vertical reinforcements values in the 11 walls that comprise elevation SW02 on level 1, but really in reality we're not going to detail walls as such. So what we would need to do then is to start rationalizing the design. So we would have to go back to design, to elevation view, for example selecting, perhaps creating another design setting and starting to lock in the reinforcement, and then essentially performing design checks. So the rationalization process that we would perform using column groups in column design, we would start doing the same thing using design settings in the elevation view or in 3D. Let's collapse this. If we zoom in, we see, okay, N12's at 200 vertical, 12's at 155 each face. Make the text smaller. So calculating different reinforcement for each.